Welcome to the video on principal component analysis. So what is principal component analysis? In short, PCA. So basically it is a method to reduce the dimension. We'll see what it means. So some of the data sets can have millions of records and hundreds and in some cases thousands of independent variables or predictors. So, but what happens is when you have such a data set with so many independent variables, such a large number, it can result in multi-collinearity. What multi-collinearity means is that some of the variables, a lot of variables, can be strongly correlated to each other. What does that mean? When they are strongly correlated, that means all these correlated variables are explaining the same information in the data or same information in the model. So it actually becomes unnecessary for us to include all those strongly correlated variables, right? So multicollinearity results in having many insignificant predictors for the same reason, because all these strongly correlated variables are explaining the same information. So one of the variables is, or maybe two of them are good enough to explain all the that particular part of the information of the model or the data set. The rest of those strongly correlated variables become insignificant. So we can get rid of those insignificant predictors. So particular component of the model may be overemphasized. What it means is that if you are having too many strongly correlated predictors in a model, then basically what these predictors are doing, they're explaining the same information, right? And that information, what particular component, that's what we mean. So the model may overemphasize that particular component because we have too many predictors explaining the same component, giving more importance to that particular component of the model or the information of the model. So this also leads to complicating a model with the inclusion of unnecessary predictors, as we discuss here, that all these strongly correlated predictors are unnecessarily making our model too complicated because we have got too many variables. So we don't need the aim of whenever we are building a model, we should always try to look for simplicity, as simple as possible. So when we are interpreting the model, the interpretability becomes easier with less number of variables. So what PCA does is it reduces the number of insignificant variables, and then it reduces the complexity of the model. Obviously, when you will let go of those unnecessary variables, the simple model becomes very simple, and therefore the interpretability becomes easier, right? So this is the main. So how does PCA work? So there are basically three simple steps. So first, what we do is we normalize or standardize the data. We'll see in the next slide what it means. Then what we do is we compute the principal components. That is why it is called principal component analysis. So we will see what principal components are in the next slides. Then what we do is we use these principal components to reduce the dimensions of the data set. That is the main purpose of this PCA. So what is normalize or standardize the data? So basically we need to standardize all the predictors so that all of them can have the same scale. What it means is, we'll look at it with one example here. Let's say in a data set we have two variables. One is age. Now age is measured in this two digits, right? 45 years old, 60 years old, 70 years old. And another variable is salary. Salary is measured in thousands, right? So 67,000, then 90,000, 100,000. Now if you look at these two values, the set of values, these are in tens, right? And these are in thousands. So if you build a model, obviously model will this variable will dominate the model primarily because of its magnitude, right? Compared to this, it is much larger, right? So in order to do that, to build a proper model, we usually do the standardization, because then we get a good result. Because you cannot say that this variable is more significant than this, mainly because the scales are different, right? That is not the criterion here, right? Same applies to even principal component analysis also. To calculate the principal components, we need to transform all the variables into the same scale. and that's why we follow this standardization or normalization of data. So there is a formula for that, which is, let's say this is the standardized or normalized version of the variable x. So the formula is z is equal to xi minus mu by sigma, where xi is the variable itself and I varies from 1 to m, where m is the total number of examples or rows or records in the data for each variable, right? Mu is the basically mean of the variable x, right? So if this is for one variable, so we use the same formula for all the variables to standardize each variable. And what is this sigma? This is standard deviation of variable x. So what we do is we simply subtract the mean from the variable and divide it by the standard deviation of the variable. This gives us the standard value. So all the variables will have the same scale. So this simplifies our task, and also that way our model performs well, even principal component performs well. That's what it is. So let's try to understand what is principal component. So basically it is there are as many principal components as the number of variables. So if a data set has 10 variables, then it will have 10 principal components. The first principal component explains the maximum variance in the data, right? So let's try to understand it pictorially. I have just plotted of the scatter plot of two variables from the data set. It's a very simple data set. It has only two variables, salary and age. So you see these are the dots, which are basically the data points, and you see this is the first principal component and this is the second principal component, right? So the first principal component explains the maximum variance in the data. What it means is, see, the whole purpose of principal component analysis is to reduce the dimension of the data set, right? So what do you mean by dimension? Dimension means the number of variables in the data set. If there are 10 variables, then it's 10 dimensional data set. If in this case there are only two variables, so it is two dimensional data set. So, and as we saw that huge number of variables can create a lot of problem while model building, because some of them may be correlated, right? So we don't need so many insignificant variables in our model building. So you see the first component, principal component, is explaining the maximum variance in the data. If you see the data has maximum variance in this. More than 90% the variance looks like is in this direction, and very little variance in this direction. So just by using one principal component, we can actually explain maximum variance in the data set, and that will take care of our problem, right? So we don't really need this small second principal component. So as it works on reducing the dimension, so in this simple example also you can see that the two-dimensional data set has been reduced to just one-dimensional data set, because we can do with just one principal component. We don't really need this one. So to calculate principal components, what we need is covariance matrix. Covariance matrix basically explains the correlation among variables. So basically correlation covariance between two variables would mean that if the value of one variable increases, what happens to the value of the second variable? If the value of second variable also increases, that means they have a positive covariance. If the value of the second variable decreases, that means they have negative covariance, right? So if one increases and the other one increases, or one decreases and the other one also decreases, then they have positive covariance. If both are moving in opposite direction, that means one increases, the other one decreases, then negative covariance. So covariance matrix is defined as this: 1 by m x transpose x, where m is the number of records in the data set x. So x is the data set, m is the number of records. The dimension of this matrix is n by n, right? N is the number of variables. So then once we have this covariance, then we calculate eigenvectors. What does eigenvector do? It basically explains the directions of the axis, the directions of the variance, right? Basically, this is what helps us in finding this principal component actually. Because you see the direction of variance, maximum variance is in this, right? This is the direction. And then another one is this. So this is what it explains, the direction of axis of the variance, eigenvectors. Then we have eigenvalues. Eigenvalues nothing but kind of coefficients of eigenvectors. So this explains, eigenvector explains the direction of the variance, right? And this eigenvalues explain the magnitude of the variance. So yes, it is moving in this direction, but what is the magnitude of that variance in this direction, and what is the magnitude of the variance in this direction? So this is a very simple way to understand. We'll learn more about them later. So one rule we need to remember, that number of eigenvectors in a covariance, right, matrix, number of eigenvectors is equal to the number of eigenvalues, and equal to number of variables in the data. So eigenvectors, for every eigenvector we'll have one eigenvalue. So the total number of eigenvalues or eigenvectors are equal to the total number of variables in the data set. We need to remember. So let's understand how eigenvectors and eigenvalues play an important role in deciding principal components. So that same example that we saw in the previous slide, this salary and age, there are only two variables in the data set. Okay, and we saw that the variance is maximum in this direction and very little in this direction. Since there's only two-dimensional data, so the data will vary only in two directions, right? In two-dimensional space. So when we calculate the eigenvectors and eigenvalues, this is what we get, right? This is the eigenvector, okay, and this is eigenvalue. So the first column that you see is the first eigenvector. Okay, second column is second eigenvector. Since there are only two variables, so there'll only be two eigenvectors and only two eigenvalues. So you see this is diagonal. So these are two eigenvalues. So first eigenvalue is related to the first eigenvector, and the second eigenvalue is related to the second uh, eigenvector, right? So how do we know which eigenvector explains maximum variance in the data? By looking at eigenvalue. So whichever has got maximum value, that eigenvalue shows the maximum variance, right? Because eigenvalue shows the magnitude in the variance, right? So if you see between these two values, you will see this is 1.72 and this is just 0.077. So obviously this is much larger than this. That means the first eigenvector, which shows the direction of the variance, and eigenvalue shows the magnitude of the variance. So it is very clear from this example that the first eigenvector and first eigenvalue will give us the first principal component, right? So this and this together will give us the first principal component, and that's what we will see how to calculate principal component also. So the first eigenvector, so in this example we select the first eigenvector to describe the first principal component or the maximum variability or variance in the data. Now, depending on your problem, see, this is only two-dimensional. You can have 100-dimensional data. So you will have that many eigenvectors and that many eigenvalues. So depending on your domain knowledge and subject matter expert, you can decide whether you want to drop the other eigenvectors. So here we see the large part of the variance is being explained by first eigenvector itself. So we can safely drop this, and how to calculate the percentage of eigenvalue, a percentage of the which of each eigenvectors, uh, uh, in terms of how much variance they are able to explain. So that is very simple. So you just add these two values and divide each of them by the total. So you get the percentage of variance being explained by each eigenvector, right? So that's simple mathematical calculation. So based on that you can decide, like, how much percentage of the variance is being explained by eigenvector 1 and how much is being explained by eigenvector 2. So if this is, let's say, 96%, just for example, I have not calculated, but let's say it is 96% and this is only 4%. So we can, depending on our industry or field, we can decide whether 96% is good enough and we don't need 4%. So we can let go of this, and our two-dimensional data gets reduced to just one dimension, and we meet the purpose, right? So in this example, the first eigenvector explains the maximum variance in the data. Therefore, it gives the first principal component, right? So how to calculate? This is the formula. If we have a matrix, n by n, right? Matrix, then how to calculate the eigenvalue? So this is the matrix M. Okay, this I stands for identity matrix. That means all the diagonals are ones and all the other values are zeros. And this I is also n by n. identity matrix, right? And lambda is when we multiply with this, lambda will be the total number of the number of column or number of rows, right? And this will get multiplied by all the diagonal values, which is 1. So then if the, and this sign is for determinant. So if you calculate the, if you take this matrix and subtract this value from here, so and then you calculate the determinant of this, if it equals 0, that means lambdas are eigenvalues of this matrix M. Then eigenvector for matrix M, again the same example here. How to calculate? So we know the lambda now, right? These are the eigenvalues, right? So if we, and this is E is a non-zero n by 1 vector. So if you multiply the both sides and if they're equal, right? M into E is equal to lambda into E. If lambda is the eigenvalue, then E becomes our eigenvector. So that's as simple as that, you know. So let's look at the principal components calculation, how to calculate. So to calculate principal component, what we need is we need to standardize our data, which we saw in the earlier slide how to do it. So we take the matrix of our standardized data, and then what we do is we having calculated eigenvector in the previous slide we saw, right? ME is equal to lambda E, right? So where M is the n by n matrix, E is a single eigenvector of dimension n by 1, and lambda was your eigenvalue, corresponding eigenvalue. So principal component is calculated as Z into E, the standardized data Z multiplied by that eigenvector. So this we with this formula you get only principal component of this particular eigenvector. So if it is first eigenvector, then you get first principal component. So here, so you have to repeat this process for every principal component for every eigenvector. When you do this, you get M by 1 matrix. So what you get in the, if you expand this formula, you get this. So first principal, this is, let's say this eigenvector is for the first eigenvector. So we get first principal component. So it is E11 Z1. So Z is like, Z is by M by N matrix, right? M is the number of records and N is the number of variables. So you get the first value, and this is you getting M by 1 matrix. So it will have M rows and 1 column only. So each column will contain each row will contain one principal component, right? So E11 is what? The first value of this eigenvector, right? First eigenvector. The second value of first eigenvector, and n value of nth value of first eigenvector, right? So it gets multiplied by each column actually, right? N is the column. So this is how you get. So the eigenvector values are getting multiplied by all the variables in the data, standardized data. That's what you're getting. So then again, if you do it for second principal, in our example there are only 2 vectors, so you will have only 2 principal components since there are 2 variables, so only 2 eigenvectors and 2 eigenvalues. So you see, this is the first value of second eigenvector, second value of second eigenvector. So likewise, both are same. Okay. So this is how you calculate principal components, and this was the example we saw, right? So this is our first principal component, right? This one, first one is this, and this is our second principal component, this. So this is how you do the process. So let's see how to project data onto principal components. So once we have calculated PCs that we saw in the previous slide, we project the data on PCs. How to do it? PC means principal components. So now principal components become our new axis. That's the whole purpose, you know, because now we have reduced dimension. So in our example, we take only the first principal, right? We have the example of two data which has 2 variables, salary and age, right? So we calculate, what we do is we calculated the principal component and then we take the first principal component, right? Because that explains the maximum variability in the data. And to recover the data, how to do this? So we recover the data in its standardized form, right? Because PC only gives us the principal components, right? So we have used the standardized data and eigenvectors to get PCs. Now we will use PC and eigenvector to get back our standardized data. So this reduces our 2D data into 1D data, right? Because we are using only first principal component. If we had multi-dimensional data and we had calculated PC, perhaps we would have taken, let's say if there are 100 variables, we would have taken first two or first three or first four principal components. So then that would have reduced 100 dimensional data into just 4 or 5 dimensional data. In our example, it's 2D to 1D, right? So this is the formula we do, right? So Z recover. So this is first principal component and then the eigenvector, right? So the first eigenvector, because that's corresponding to the first principal component. And then we multiply, take the transpose, and then we multiply, and then we get our recover our standardized form of original data. So then we plot this standardized recover data along with the standardized original data. So this is what we get. See, so this scattered plot, the blue ones are basically the standardized data, original data, without any dimension reduction, without any principal component. And what you see, the red dots, this is the recovered data that we have plotted. Recovered means first we converted the data into principal components. Then from principal component, then we reduced we picked up only one principal component to reduce the dimension. And then we use that particular principal component to recover our data in a standardized form. So you see how nicely it shows here. So this is just one line. If you see that is what is expected, right? Because we are using only one principal component that will show only one direction, will move only in one direction, and that explains the maximum variability in the data. So this is how we work on principal component analysis, basically to reduce the dimension. So let's look at the sample code that I've used to create all those graphs and the example and principal component analysis. So this is the variable, like set.c to for the reproducibility. You can do it on your system; it will work the same way. So I've created one variable using function rnorm. Basically, it creates a random uh, variable in which follows normal distribution. So you need to supply how many observations you want, mean and standard deviation, right? And since and the second variable is salary, so salary has to be dependent on age, otherwise there's no point doing principal components for two differently uniquely independent variables. So they have to be dependent on each other. That's only this principal component works, right? So for that purpose, I have just used this, as a variable here, and created another variable salary, and I've added, this is your basically error term, right? Even if the two variables are dependent, there'll be an error term. So I've added one error term here, again using the same function, and so you can just check it out. When you plot, you'll get that plot which we saw in the previous slides. So then we have to standardize this data, right? Because the mean is when we standardize, the mean becomes 0 and SD becomes 1, right? That's what happens when you normalize the data or standardize the data. So age, standardized form. So age minus mean divided by standard deviation. Then salary has been standardized again or normalized again. Salary minus mean of salary divided by SD of salary. So just transform these two variables into a matrix, right? Cbind, using cbind, you combine them column wise and turn this into a matrix. Then m row, n row, we calculate this for different purpose. So this is your your covariance matrix, right? Remember 1 by m into uh, x transpose into x, right? That's what we do. So x is matrix, so matrix multiplication, t is for transpose, and 1 by m is the total number of rows, right? So, and sigma is basically a general convention. We use sigma, actually the sign sigma, but I've just written sigma here. In R, that's what you do, and basically sigma is used for covariance matrix. So there's a function called SVD in R, which will calculate eigenvectors and eigenvalues for you. So you don't need to do a mathematical calculation. You just use this SVD function. Inside you put this covariance matrix, and it will give you, this particular variable. So what you do is you take this value, and you this is your eigenvalue basically, right? and this is your eigenvector. So there are two components in this. One is D, one is U. Both are small. So D stands for eigenvalues and U stands for eigenvectors, right? So this is what it is. So then what you do is for all components you just multiply this standardized data with this U eigenvectors, right? Matrix multiplication. You can do it one by one also, like since there are two variables here, right? So this will have two eigenvectors. So you can do one by one also, or you can do at a time. Then it will give you the matrix of. So it will calculate all the principal components. So if you do this vectorized version, right? So first principal component of this, so it will have two columns, right, for two eigenvectors. So first principal component is this first column and second is second column. Then we recover the data, right? How to recover? Now we have calculated the principal component. We need to recover the data from principal component. So what we do is we take this because we are reducing a dimension, right? So now we are getting rid of the second dimension. We just want first principal component. So we multiply the first principal component with the first eigenvector, transpose of first eigenvector, and then you get the actual, the recovered data. So when you plot, you get this, right? We saw in the previous slides. It's very small here, but you can check the previous slides. So these are the blue points are basically your standardized data points, and this red line is your first principal component, right? The recovered data from first principal component. So the dimension has been reduced to just one line. One line means one dimension, right? And why we are plotting in two dimension, because we need two dimension to plot. But if you turn the first principal component as first axis, then all the points are falling on the axis itself, right? So it becomes, instead of two dimension, became one dimension. That's what it means. Then you don't need to do all these calculations. This is just to show you how it works. You don't need to do all this coding here. R itself has a lot of functions. If you, at least it has two basic functions for principal component analysis. One is called PR comp and another one is called PRI and print comp. Right? Both are for principal component analysis. So you can straight away use these functions and they will do everything for you. And there are many packages also available, which you can install on your R and use them, and they have their own principal components, principal component analysis with nice graphics and all. So that's all I wanted to say. Thank you so much. If you like the video, please like, share, and subscribe.